Yeah.
Is that good? Good? Okay. This works. Thank you everyone for being here. Today I would like to use these 10 minutes also to show you our recent work on transmission neural networks, which I'm very excited about. It's because it links naturally the various transmission model with neural networks. This is joint work with Professor Keynes at McGill University. So I will start by introducing what I mean by various spread on networks, and then I will use a transformation technique that transfer that equivalent representation into a neural network representation. Afterwards, I will show you how to use these to briefly mention that how to use these to establish epidemic threshold conditions and derive continuous time network epidemic models. And then in the end, I will show you the basically says the transmission neural network are universal function approximators. Consider a network with n nodes where each node represents a person. A person has two states, whether being healthy or being infected. The probability of person I being infected at time k is denoted by pik here. And each link is called a physical link, where it's defined if two persons are within each other of the radius for at least a certain amount of time. And then on each physical contact link, multiple variables can be transmitted across. And I use Aij to denote the number of variables that's sent into the common space from node j to node I. And then I use Wij here to denote the probability of each of these variables that are successfully reset by node I that were sent from node j. With that setting, we can write the one-step prediction of the probability of infection. Where here on the right-hand side is basically reads as the probability in the narrow of the variables reaches node I at time k plus 1. And here the product is taken with respect to j in all the neighborhood of node I, including itself. Here we see that the assumption are that the variables are transmitted independently, also independent across links. Note that the homogeneous transmission probability case was actually studied earlier by these authors and their collaborators. To facilitate our analysis, I introduced the state transformation, which is monotone and bijective, that we essentially using a different ISI notation to represent the state of node I by taking the negative log of 1 minus the probability of the infection. This as actually is the Shuang information of node I is being infected at being healthy at time k. And then we take log on both sides and take negation on both sides, which then give us this very nice form, which we call it a transmission neural network. Here the psi is the new activation function is a tunable log sigmoid activation function, takes the parameter w ranging from 0 to 1. When w equal to 0, this works as if it's a no pass. When w equal to 1, this represents a full pass. When w between 0 and 1, this is a partial pass. There are other nice properties, such as this function is concave in x, and we can write explicit derivatives of this function with respect to both variables. And this is crucial in our further analysis. To summarize, when we look at the transmission neural network from a node I, it takes activated input from the neighbors, where the activation function are really on the links and has a different activation intensity characterized by the parameter w. And each node has a state, which is the information content. And then node operation is simply a linear operation, a summation. Different from the standard view of neural networks, where the activation function are primarily associated with nodes or layer of nodes. Here, the conceptual difference is that the activation function should relate to links. And that actually has very nice biological inspirations. If we look at the chemical synapses connection between two neurons, the presynaptic neuron after excitation actually send a large population of neurotransmitters into the synaptic plaque in the middle. And then each of these neurotransmitters can bond with certain probability the receptors on the postsynaptic neuron, which then causes the further activation of the postsynaptic neuron. And as you see with simplifying assumptions, this can be suitably characterized by the same various spread dynamics that we start with, which is an equivalent representation of the transmission neural network that we discussed. And such a unit can be easily incorporated into the graph neural network setting, recurrent neural network setting, or feed-forward neural network setting. So I want to spend some time on the activation functions that are tunable associated with the transmission neural networks. There could be multiple choices of them, depending on your choice of the state and your constraint on the states. One is the T-log sigmoid plus, which extends the standard ReLU activation function. And the other is tunable soft ifan, which extends the standard soft plus activation function. So this basically says when we take the state to be the negative, the information content, then the activation function we get will be the double mirror of the T-log sigmoid function we started with. And it has this very nice form. Looks like a soft plus function with some offset, which can have negative output. And then one last is activation function is a tunable sigmoid function, which is the partial derivative of the T-log sigmoid with respect to x. And it has nice properties because the activation level is actually correspond to the parameter w. When w equals 0.5, this is then the standard sigmoid activation. We can use these models to simplify the analysis on epidemic threshold. If we ask the question, are the epidemic going to, the probability of infection going to 0 after several steps? And we show that when the eigenvalues of this matrix are less than 1 in absolute value, and this would hold regardless of your initial conditions. And here, this matrix is simply, here means the element-wise product of these two matrices. And A is the correspond to the matrix where the number of particles that transmitted across the links, and W is the transmission probability matrix. Specializing this to special cases where the recovery rate is uniform by delta, and the transmission rate is uniform, beta, and then it gives you the standard, well-known threshold condition for epidemic spread. This slide shows you that we have a nice continuous time version of the transmission neural net with further assumptions on the transmission probability, Wi. Roughly here, it says that the transmission probability should scale roughly linearly in the time duration for the transmission. And then with this assumption, taking the small time limit, we then have a continuous time representation of the same model. And use the state transformation, which then further gave this new representation. It's actually the standard network SIS model. Up to here, I already gave you a sketch how we link the discrete time various spread model with the standard continuous time various model. So this is something like surprisingly to me, missed in the literature. And this slide basically, as it says, transmission neural networks are universal function approximators. This is a particular example. But here it means that it can approximate continuous functions to arbitrary accuracy. And this is a particular example where we have one hidden layer and the d-dimensional input, scalar output. And this is the structure. I want to highlight that here we don't, we fix the bias B, which is different from the standard universal function approximation result, where B is arbitrarily chosen. Okay, so I want to conclude my talk here. I showed to you the new neural network model, which we call the transmission neural network. They are universal function approximators. They have very nice properties because they can connect with various spread model naturally and has biological neural network motivations. And then this yields simplified analysis for various spread on networks. And there are lots of interesting questions moving forward in learning epidemics and in biological network modelings. So I list a few here. If you're interested, feel free to reach out to me. Thank you.
You have time for questions? Thank you for the talk. I'm not really aware of the literature, but I would like to understand a little bit What is the real application of the transmission neural net? I mean, is it something that is closer to epidemics or something that is closer to machine learning? What is right now the holy grail that is solved by transmission neural nets?
Oh, thank you so much for the question. So first, I want to mention this is I don't think this is something exists before. So and then to your question is that it can work both in the epidemic setting or in the learning setting. In the learning setting, one has this very nice feature of tunable parameters, tunable derivation functions. You can have a bunch of arbitrary choices of a continuous set of activation functions, which is very nice. And in terms of epidemics, I think this is a further direction that I'm going to explore, and how, because of this nice connection with epidemic networks, with machine learning architecture. So I was thinking maybe we can use the machine learning training tools to actually predict and estimate the various threat using this connection. So that is, yeah, that is my current thought on that. Yeah.
We'll take one more question.
Yeah, thank you. I wonder, is it possible to use SIR network to design new kinds of neural networks?
I think that's a good question. The reason that I think this would incorporate very nicely. This setting would incorporate very nicely with the setting with SIR setting. But one needs to be careful what we mean by the recovery state. I think like most people think about the recovery state is actually node state, but I think it's more natural to think about the recovery state as a link state. When you recover, you don't send viruses across the networks, and you don't receive viruses, or you receive viruses, but you don't get infected. And so that's my view towards how to incorporate the recovery state into this setting. Yeah.
Great. Okay, so let's take further questions in the break and move to the next talk.